Hi, this is Algebra 1, Lesson 8-5, Linear, Exponential, and Quadratic Models. In this lesson, we'll be able to determine whether a linear, exponential, or quadratic function best models a data set. So now that we have learned a linear function, exponential function, and a quadratic function, we want to compare them in different scenarios and see which function would best fit the data. Okay, so remember the characteristics of these functions. Linear will have basically a line, straight line, right? And exponential will have a curve that grows or decreases exponentially, and the quadratic function goes both ways, either up or facing down, right? Okay, let's look at model and discuss. JC and Emma use different functions to model the value of a bike X years after it is purchased. Each function models the data in a table. So, if you look at the table, we see some points, 0, 500, 1, 485.2, 2, 472.13, and so on. JC's function is negative 14.2x plus 500. Okay, it's a linear equation. Emma's function is f of x equals 500 times parentheses 0.85 to the power of x, where it's an exponential function. So just by looking at the data, you might not be able to gauge how the data are scattered. So you want to graph them in a graph. Let's use a graphing calculator. We're going to use Desmos just to plot the points, but you should be able to plot the points by yourself. Okay, so let's do 0, 500. Whoops, did I put 0, 500, and then 1, 485.2, and then 2, 472.13. Okay, you just put in all the points with parentheses, and you'll see that your grid line isn't the best looking at this, so I'll show you how to adjust so that you can see it clearly. You want your x-axis to be a smaller number, a little spread out, and then your y-axis could be spread out a little bit more. And now you can see how it's spread out. Does this look like a curve or a line to you? What is it closer to? Now it might not have a perfect line or a curve, but you can see whether or not it's going to follow the same pattern or like an exponential function, or it's going to draw a parabola, right? So just by looking at these points, it looks like it's closer to a line. You see that? It looks like the points are decreasing at a constant rate instead of a curve, right? So if it were an exponential function, we would expect the points to decrease a lot faster than these points, right? So, part A. Why did JC and Emma not choose a quadratic function? So neither of them are quadratic. You know how quadratics look like a parabola, right? A quadratic function wouldn't make sense because the bike's value is always decreasing. It's not increasing at some point, right? So you know for quadratic function, it has to increase at some point or decrease at some point where you have an increasing and decreasing for both increasing and decreasing in a parabola, right? Because we're looking from left to right when we're talking about is the value increasing or decreasing. So quadratic function has both increasing and decreasing functions unless you limit your domain. Okay, but that would be enough reason for part A because it is always decreasing. So you can write that a quadratic function wouldn't make sense because by its value is always decreasing and there's no point where it starts to increase. All right, part B, whose function do you think is a better model? Explain. We already talked about it. But whoever has which type of function? Whoever has a linear function would be a better model. Okay, so just by looking at their types of equation, we know MS function is exponential and JC's is linear, right? So that's exponential, that's linear. So we know JC will have a better model because it stays closer to data points when you graph a straight line. Okay. So why don't we check? Let's graph both of the functions. So this is JC's model. F of x equals negative 14.2 x plus 500. Okay, that looks pretty close. What about MS function? MS function is 500 times 0.85 to the power of x. Not really. It only matches the first point, but not the other points, right? So you could visually see how closer JC's function is compared to MS. So you can say JC's function is a better model because it stays closer to the data points. Part C, do you agree with this statement? Explain why or why not. Let's look at the statement. To ensure that you are finding the best model for a table of data, you need to find the values of the functions for the same values of x. What does that mean? To ensure that you're finding the best model, so how would you know that you have a best model for a table of data? You can graph it and visually see, but it says that you need to find the values of the functions for the same values of x. So is that what we are doing? So it is helpful that we find the values for the functions for the same values of x, but so not all data points might be perfectly fit into a line, whether or not it's a linear line or exponential function or a parabola or quadratics, right? But yes, it is helpful that we find the values of the functions for the same values of x. So that's where we can start. So if you look at x, when x is equal to 0 or 1 or 2 or 3 or 4, is it close to the value? That's what we're looking at. So yes, that would be agreeable. That would make sense. So let's write that down. When you are comparing multiple models for a set of data, it is helpful to find the values of the functions to compare and determine which is the best model. So in order to compare them and determine which is the best model, yes, we want to compare the values. All right, so this lesson's essential question is, how can you determine whether a linear, exponential, or quadratic function best models data? Let's look at example 1. Determine which function type represents data. How can you determine whether the data in the table can be modeled by a linear function? So now we want to see if the data could be modeled by a straight line, a linear function. So first, we want to think about the characteristics of a linear function. It is a straight line in graph, which means it has a constant slope, okay? And the equation form should be y equals mx plus b, right? There are different forms of linear equations, but this is the slope-intercept form, the most common form, I should say. So first, we wanted to see the data. So the data in the table says -2, -1, -1, 0, 3. We want to see the differences between the x values and the y values to figure out the slope. See if they are constant, right? All the values for x is added by 1, and every time the values for x is added by 1, the values for y increase by 2. Right? So the differences are constant, right? So linear function best models the data when the first differences are constant. So is this a good data for a linear function? Yes, linear function would be the best to describe this data. Okay. And how can you determine whether the data in the table can be modeled by a quadratic function? However, let's analyze the second differences. What is the first and second differences? First differences, so now look at, so this is one data, and then now we have different data points, right? But the x values are the same, we just have different y values. If you figure out the differences, they're not constant, they're not equal. So we want to check if it may have a pattern. It may have the same difference between consecutive first differences. So 10 minus 6 equals 4. 14 minus 10 equals 4. 18 minus 14 equals 4. So is that okay? The differences of the differences are equal. So this is when the second differences are constant, and that's when we say a quadratic function may best fit the data. Okay? Although the perfect quadratic function will have powers of 3 in this case, so 3 and 9 and 27, and then it increases a lot faster. It may have transformations, right? Like A, B, and C that we've looked at, that transforms the graph a little bit narrower or wider or flips the sign, and everything like that, right? So this is one way to figure out if it is best fit for a quadratic function. When the first differences are different, it means it's not a linear function, okay? And then second differences, you figure out the differences of the differences, okay? And if they are constant, we can say a quadratic function would be the best, okay? Now, how can you determine whether the data in the table can be modeled by an exponential function? How do we know if it would be best for exponential? So now we find the first differences, second differences. Okay, this is another set of data. First differences are not equal. Second differences are not equal either. Now what do? Look at the ratios of y values. Okay, don't look at first and second. We're going to look at the y values again and figure out the ratio. 2/1, 4/2, 8/4, 6/8, are they the same? Okay, we're going to look at the ratios of them, not the differences, the ratio. So you divide them, and they're the same. So this is when the exponential function is the best. Okay, so these are the simple 3 methods to check whether or not linear function, exponential function, or quadratic function would best model the data. You need to know how to find the differences, and then the second differences, which is the differences of the differences, and then ratios of y values. Now, if you figure out, but it needs to be in order. If you have a constant first differences, then it's a linear line. And then if that's not a constant, if that's not the same, then go to second differences. If the second differences are the same, then it's a quadratic function. But if that's not the same, then go to ratios. So that should be in order. First, check if it's linear, and then you'll check if it's quadratic, and then you'll check if it's exponential. Okay, that's the order. It's not exactly the order that we learned, but this is the order that you should check if the function, if the data set is best for those. Okay, so let's look at try number 1. Does a linear, quadratic, or exponential function best model the data? And explain. Use the method that we just looked at in example 1 and see if you can get them correct. So pause the video and come back when you're ready for answers. Okay, are you ready? So, before we reveal the answer, let's look at it together and see how we can do it together, how we can solve it together, right? So first you want to check the differences of the y values. X values are increasing by 1. Just check if the x values are increasing by 1. There may be a table of values where the x values are not increasing by 1. If the x values are not increasing by a constant term, then you need to adjust the data. But in this case, we're safe. So let's just look at the y values. So the first difference is -5 minus -2 is -5 plus 2, so that's -3. Okay, and then between when x is 1 and 2, the difference is -14 minus -5. So -14 plus 5 is -9. Okay, and then -29 minus -14 is -29 plus 14. So that is 15. -15, right? No. Yes. So -15, and then -50 minus -29 is -50 plus 29, so that's -21. So the first differences are -3, -9, -15, and -21. They're obviously not equal, so let's find, so it's not a linear function. And then the second differences, we want to figure out the differences between the differences. So -9 minus -3 is -9 plus 3. That's -6. Okay, -15 plus 9 is -6. -21 plus 15 is -6. So yes, the second differences are the same. So this data set is best modeled by a quadratic function. And we want to explain, so let's say the second differences are the same. So part A is quadratic, and it's because second differences are the same. Let's look at part B. So first of all, let's figure out the first differences. Okay, so 12 minus 4 is 8. 36 minus 12 is 14. So obviously they're not the same. So linear equation is not going to be the best fit model. Oops, this is 24. Let's continue. 108 minus 36 is 72. And 324 minus 108 is 216. And then let's look at the second differences. 24 minus 8 is 16. 72 minus 24 is 48. And 216 minus 72 is 144. So obviously the second differences don't match up either. So it's not a linear, it's not quadratic. Now let's see if there's a ratio. So if it doesn't fit any of them, then we can just say it does not have a strong relationship, okay, for us to model with an equation. But let's check the ratio of the y values. So 12 over 4 is 3. 36 over 12 is 3. 108 over 36 is 3. And 324 over 108 is 3. So now we see that the ratios of the y values are the same. So we can say that the exponential function is going to be the best function that fits the data set, because the ratio of consecutive y values are the same. Okay. All right, let's look at example 2. Choose a function type for real-world data. The owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. How can you use the data to estimate the cost of the bubble wrap for a picture with a length of 75 inches? So if you look at the data, we see the length and the bubble wrap cost. So we can say that the length will be our domain, and the bubble wrap cost would be our range. And we see that the domain increases by 6. Make sure they are constant. Otherwise, our ratios and differences may not be accurate. Okay, and then the range, now we want to find the first differences. And then the second differences, and then the ratio if we need to. So figure out the first differences in step 1, and they're not constant. Second differences, they are close, but they're not exactly the same, but they're roughly close to each other. They're roughly constant. If you want to check if the ratios are going to be better, if you figure out the ratios, they're going to be different as well. So the second differences will be a close data. Even though it's not exactly all same, we can say that 0.10 and 0.11 are pretty close. So if they're roughly constant, we can say, oh, the quadratic model will best represent the data. Because in real world, there is not going to be a perfect data set. Remember that. So if in example 1, we did look at perfect data set for each examples, but in real world, they're not going to be perfect. So as soon as we see a roughly constant date, like differences or ratios, then we can say, oh, this model is going to be the best. Okay? So in this case, quadratic model will best represent the data. So you can write a quadratic function that represents a data using a graphing calculator. You can figure out the quadratic regression. So if you look at your values are increasing, increasing, increasing. So it's probably gonna be, the point is probably gonna be, the vertex is gonna be less than 6. So if you look at the quadratic function, it's very different. It's it's similar to exponential, but it's different because exponential functions does not grow like that. It grows a lot quicker, or yeah. But the patterns are the graphs look like they're about the same, but they're not. Okay, they're different. All right, they're very similar though. A quadratic function does only have a power of 2, and that's the end. All right, looking at the quadratic function, you can substitute x equals 75 into the equation because that's what we want to get, right? You want to figure out this one. Oh, I didn't explain how to write the quadratic function. Do you remember from the quadratic function you have the form y equals ax squared plus bx plus c, right? Using the form of quadratic function, you'll figure it out using the points. If you have a vertex, that would make it a lot easier. So if you can figure out a vertex, that'd be great. But in this case, if you can only estimate, oh, the vertex is gonna be when x is equal to 0 or smaller than that, smaller than 6, right? So then if you plug it in for, just pick 2 points. If you plug in your values of x and y into the equation, you'll get some equations with different values of x and y. And if we assume that we don't have a constant, because if there's no length, we probably have no cost, right? Then we can say, oh, c is 0. Just looking at your situation, you can figure out some information that are not explicitly given. So looking at that, you can plug in some values. 0.1 is equal to a times 6 squared plus b times 6. And then write another equation using another point. 0.31 is equal to a times 12 squared plus b times 12. And then using the systems of equation, you can figure out a and b. And that could be roughly your a and b, okay? Or you can use the graphing calculator to plug in all these points and then figure out the quadratic function, quadratic regression line, using those points, which would be a lot quicker. So you enter the data sets, just enter all the points, and then you're going to use the quadratic regression feature. If you click it, you can, the calculator will do the job for you, and these are the information that the calculator gives. And if you substitute x equals 75 into the equation, you will get 9.010, and that's going to be 9.01. Okay, so you do need to use a calculator. Okay, so if you use Desmos, you can first plug in all the points in your data set. You would have to use a graphing calculator. So it is best if you have a graphing calculator like this, okay? But if you don't have a physical graphing calculator, this is not the best. It will be easier to use a graphing calculator, but you can still go to the online graphing calculator and plug in all these points. You just have to fill in the quadratic form, okay? And then you might have to just adjust it by yourself. Okay, y equals ax squared plus bx plus c, that's the form. And then we're going to adjust. This is when all of these a, b, and c are 1. So we want to adjust where c may be, b may be, and then a may be, it may take you a long time to figure it out. Because these are very small numbers, right? So you might have to make it even smaller manually. So if it gets smaller and smaller, it gets wider. So there we go. So now we have an accurate one. So you might have to change the minimum and maximum, because this is a really small value. So all your y values are small, right? So you need to look at the y values to determine whether your minimum or maximum falls where, right? So that one looks more like it. You might have to move a little bit. So it's definitely not negative. It's a positive, but we want it to be wider, right? So A might need to be smaller, 0.5. Let's do that. Oh, there we go. It'd be smaller than that, bigger than that, 2.5. 1.6, 1.8. Okay, that looks more like it. So this may take you a lot more time than you may need, and it may not be as accurate as the graphing calculator, because if you plug it into the graphing calculator, everyone's going to have the same equation, okay? But if you use the online graphing calculator, you do have to adjust the A, B, and C manually to make it as close as possible. So that's the equation we got, as close as possible. So I have 0.0018 x squared plus b, which is 0. So there's no bx, okay? There's no second term, plus 0.01, okay? But if you use the graphing calculator, as you can see in the textbook, it will give you very, very small numbers, and it will be a little bit more accurate to your points. And then you can substitute 75. If you substitute using the graphing the equation that you figured out manually from the online graphing calculator, it should still be close. So look at 75, and you can plug it in. What's A? So 0.0018 times 75 squared plus C, 0.01, is about 10.135. Is that close to our answer? Yeah, it's not too accurate, but it's still close. There's a big margin. There's a $1 of margin of error, but that's fine. Okay, don't worry too much about how accurate it's gonna be. You just need to know how to do it. All right, so try number 2. Try a different set of data. Determine whether a linear, quadratic, or exponential function best models the data. Then use regression to find a function that models the data. So if it weren't quadratics, you could probably use the linear functions, the linear forms, equations, and exponential function equations. Or you could also use the same method. It might just be more accurate or easier to use the forms of linear function and exponential function equations. Okay, so let's see if you can try by yourself, and we'll talk about it again when you come back. Okay, are you ready? So what's the first step to check if it's any of these functions? You want to first check the first differences, and then the second differences, and then the ratio. Let's first check the first differences. So you always subtract what's later, the point that's greater on the right minus the one that's on the left side of the function. Okay, so 89.5 minus 100 is equal to negative 10.5. Okay, 78.9 minus 89.5 is negative 10.6. 68.4 minus 78.9 is negative 10.5. 57.8 minus 68.4 is negative 10.6. And I would say they're pretty close, right? They're all decreasing at a roughly constant rate. So because our first differences are pretty much close, we can say that the linear function best fits the data. And then we're going to use regression to find a function that models the data. So in this case, you can use this point as the y-intercept. And then you can pick another point to get your slope so that you can get an approximate linear equation. But depending on your point, you might get slightly different slopes, but that's okay. It doesn't have to be that accurate. It's probably going to be 0.1 accuracy, right? So if you get a slope between these 2 points, you get 89.5 minus 100 over 1 minus 0. So that's negative 10.5 over 1, which is negative 10.5. Okay, so if you get if you pick these 2 points, you'll probably get negative 10.6. They're pretty close. Okay, so you can write first. Let's write which one. So linear would be the best fit, the best model, and then your equation could be y equals negative 10.5 x plus 100. Okay, now if you use the regression feature in the graphing calculator, it's going to give you a more accurate equation where y is equal to negative 10.55x plus 100.02. But this is pretty close enough, okay? So that's okay, as long as you get a close equation just for this lesson, okay? As long as you have a close equation for a regression line, that's fine. You're correct, as long as you know how to do it, okay? Let's look at example 3. Compare linear, exponential, and quadratic growth. The graph shows population models for 3 cities based on data over a 5-year period. If the populations continue to increase in the same ways, when will the population of city C exceed the population of the other 2 cities? Let's look at city C. It looks like it's a very slowly increasing line, but it is an exponential function, and exponential functions will speed up really quickly later. City B has a quadratic function, city A has a linear function, right? So you can imagine it keeps growing, that way, And then this one will have a curve, right? And then at some point, city C is going to exceed the populations of the other two cities. So let's look at some table of values. Okay, the population of city C is greater than those of city A and B. If you look at x equals 11. So using your function, you can figure out the tables of values for future years. In this graph, it only shows the years from 0 to 5, and city A is not even, it doesn't even go all the way up to x equals 5, right? So yeah, it's cut off. So if you keep drawing the graph, then you'll be able to see where it exceeds. But looking at the table of values, you'll be able to see it numerically, right? So by year 10, you can see that city C is going to exceed city A's population, or city B's population, and it's going to be equal to city A. But in order to be more, you'd have to go over that. Okay, so using the table values is method 1. Method 2, you're going to use a graphing calculator to determine the points of intersection. Basically, you plug in the functions into a graphing calculator. Let me erase all that. And then you just plug in the functions into it. So city A is going to be f of x equals 3.2x. City B is going to be g of x equals 0.25x squared. And then h of x is equal to 2 times x 2 to the power of x minus 5. Okay, so how can I? The y's are in decimal, so you have to adjust your y values in order to really see your graph accurately. Okay, so let's change the color for that so that we can clearly see which one's which. Okay, city A is going to be red. City B is blue in your textbook, so I'm going to do blue. City C is going to be green in your textbook, so let's use the same colors. So city A is going to be linear like that. City B is blue, and it goes the curve goes slowly over. And then city C, it's very slow in the beginning, but it grows exponentially fast. So at this point, it already exceeds the y values for both city A and B, right? So there we go. So that's right at 10, they're the same. With city A and city C's population will be the same. And if you go slightly over 10, then that's when city C begins to have more population than any others. Okay? So this is method 2, using the graphs to visually see it. In the graphing calculator, you can also solve for the intersection point. So if you have a graphing calculator, come talk to me. I'll be able to show you in detail, step by step, how you can do it. So the final interpretation of your answer would be after 10 years, the population of city C will exceed the population of city A and city B. And it will continue to outgrow the other city because it is growing exponentially. Okay, let's look at try number 3. Compare the functions f of x and g of x and h of x. Show that as x increases, h of x will eventually exceed f of x and g of x. So you can use both methods. Method 1, you can use the table of values, And method 2, you can use the graph to show that h of x will eventually exceed, because h of x is an exponential equation, right? So exponential equation outgrows other equations at some point. So see if you can try showing it by yourself, and come back when you're ready for answers. Okay, are you ready? So first, you can graph them or use the table of values. I'm going to graph first and show you visually. So in Desmos, you can plug in the functions and visually see them. You can set your domain and range to be between these numbers. Your x-axis should be smaller than your y-axis because the values get it doesn't take long for the y values to go super big, especially for the exponential function. So if you zoom in, right, this is how it really is in a big picture. But if you zoom in, you can see that it starts with the g of x being the first, the biggest one, right, in the beginning. And then up until here, you still see that g of x is going to have bigger y values than the other points on the other graphs, right? And then at this point, blue exceeds, and then green exceeds again. So g of x was a little bit was smaller than the y values of g of x were smaller than f of x for a short time. You see that? Between 0.5 and 1, and then because it's curved, and then it's going to exceed again. You see that? Yeah. Look at the purple one. It looks like it's out of the game in the beginning, right? It's way lower than the other two lines. But if you keep going up, there is a point where h of x exceeds f of x, and that's at when x is 3.717, and that's going to be exactly, the y value is going to be 13.151. And after that, h of x exceeds f of x. And then, if you go further away, then at this point, when x is equal to 6.413, that's when h of x finally meets the y value of g of x. And then it exceeds when it goes greater than that. So pick a point that's greater. So if you pick maybe when x is equal to 7, right? Then 128. H of x is going to be 128. And then the other values are going to be a lot less. So now let's look at the table of values. You can go to settings and then click this icon to create the table for each function. And then you can see that they stop at 2, so you can keep moving. So let's pick when x is equal to 7. F of x is going to be 23. G of x is going to be 101. And h of x is finally going to be 128. So it already exceeds the other two graphs by the time x is 7. Okay? To be exact, when x is equal to 6.4142, maybe. So if it's greater than 6.414, then your y values of h of x already exceeds the y values of the other graph. So let's write that down. Okay, so you can write this down. Initially, g of 0 is greater than f of 0 is greater than h of 0, like we talked about, right? That's g of 0, and then that's f of 0, and that's h of 0, okay? And obviously, 3 is greater than 2, and that's greater than 1. So g is starting off strong. But eventually, h of x will be greater than f of x and g of x for larger values of x. So for example, we saw that when x is 7, f of 7 is 23, g of 7 is 101, and h of 7 is 128. You can also explain that in a graph as well if you are willing to write down and draw the graph. But algebraically and with words, that should be enough. Okay, so that was a lot of comparing the functions. So please keep in mind of the characteristics of each one. That would be super important in this lesson. Let's summarize our lesson. So linear, quadratic, and exponential functions have different characteristics, and in order to figure out which best fits the data, you have different methods to figure out which one. So first of all, you want to check the first differences of the y values, and if they're the same, then linear equation will best fit the data. But if that's not constant or the same, you want to find the second differences, which could be figured out by subtracting your first differences. And if that's constant, then you know quadratic is going to be the best fit line. But if none of them makes the same number, then you want to check the ratios of the y values. If the ratios of the y values are the same or they're pretty close to each other, then exponential function would best fit the model, will model the data the best. So looking at the graph, you'll obviously see a straight line for linear function and a slightly curved line for quadratic and a big curve for exponential function. Okay, so you know that the exponential function will eventually outgrow all the other functions. All right, guys, that was lesson 8-5, linear, exponential, and quadratic models. I know there were a lot of things that needed to be discussed further, so if you need more help or if you have any more questions, please feel free to ask me. Otherwise, let's continue with the next lesson in the next topic in the next video. Thanks, bye!